All right, I want to take a moment to introduce section 4.4, the Central Limit Theorem. And section 4.4 is really just continuing to build off what we have been doing. But the main idea with the Central Limit Theorem is that if we keep taking samples of different sizes and keep working with those, we can get a population that isn't normal to kind of translate into one that becomes normal. So we're talking about samples instead of just individual occasions. And there are a few different things that can happen. We'll deal with means and we'll deal with proportions for the start. But essentially, the standard error, mu sub x will be the mean of our distribution. And then we have a new player here, sigma sub x, and that's the standard deviation of x as we're drawing these sample sizes. And this value mu of x, or mu sub x, that's going to just approach mu. So our mean for our population will approach the mean of the population. Okay, the mean for the mean for our samples will approach the mean of the population. And the standard deviation just changes to, instead of being sigma, it's sigma over the square root of n. So this is the standard deviation of our means, or the standard error of the means. And essentially we're going to do what we have been doing. We just replace sigma with sigma over the square root of n. So that's for working with means. If we're working with proportions, things work out the same. So proportions tend to be normal anyway, but our standard error then becomes the square root of pq over n. And notice all of this is inside of the square root. So slight variations. So we'll get to some problems here, some examples. But these are going to be the new formulas, and we're still going to be doing things the way we have been, with just new versions of the standard deviation. So questions here. Maybe I'll zoom in on this a little bit. CNNBC recently reported the mean annual cost of auto insurance is $958. Assume the standard deviation is $214 and that the population is normally distributed. You take a simple random sample of 85 auto insurance policies. Find the probability that a single randomly selected value is less than $987, and then find the probability that the sample of size n equals 85 is randomly selected with a mean of less than $987. So I'm going to put some important information over here. We have mu is going to be $958. Sigma is $214. Just taking this from here, the mean annual cost of auto insurance is $958. The standard deviation is $214. And then we have samples of 85. So for the first one, the probability of just an individual value being less than $987. I said I wanted you to draw. Oh, I gotta grab over here. So I'll try to draw this here. A normal distribution. We've got 958 here in the middle. And 987 would be over here. Remember, one standard deviation would be $212. Excuse me, 214. So 987 wouldn't even be a full standard deviation away. So we're looking for this here, and this cut off 987. Okay, getting really ugly trying to use my my skills there. Okay, so the probability. So I just grab this, and I'll do some work over here. But these are normally distributed, so I can use a normal distribution. Now, 987 is that value I'm interested in. I want the area to the left of it. So I'm going to grab the mean. And actually, I think I'm going to go ahead and type it in. 958, the standard deviation, 214. And this is true because we want the area to the left of it. So for an individual value, we're talking about a probability like this. Now this is similar to what we have been doing. 0.5539. Now, what we're dealing with, the new idea here is if we take samples, we're going to have a new standard error. So the standard error is going to replace the standard error. The mean, technically, is going to be sigma divided by the square root of n. And I'm going to go ahead and type these numbers in so that when I copy and paste this, I guess I typed some of them in. We have a little different deal here. So now our standard deviation is basically 23. So 958, one standard deviation is like $981. So our new distribution, trying to draw a normal curve again. We still have 958. But now our value of 987 here for the mean is going to be over here. So we're talking about an area like this instead. Sorry, it's so choppy. So now we have x bar being less than 987 instead of x. And we're still doing the same kind of thing. We have a normal distribution. 987 is still the number that's interesting. The mean, 958. Now the standard error becomes this guy. Our new standard error replaces the standard deviation. And notice we get a little bit different value for this. 89423. So what's happening here when we're taking larger samples, it's going to be less likely that the whole sample mean is, or it's going to be more likely that the whole sample mean is less than this. We could have an individual value get out here, and that wouldn't be entirely uncommon, 55% of the time, compared to 89% of the time. Anyway, so I'm going to stop this video here, just with one example done, and then I'll probably work through a couple more examples in a follow-up video. Thanks for watching.